Now that we've learned how to solve separable differential equations, let's take a look at some real-life problems that we can solve with them. So the first example is going to be, how long does it take a cup of coffee to cool down? And I actually have a cup of coffee right here, so let me move this into the frame. I have a thermometer inside, and it looks like at the moment the temperature is about 144 degrees Fahrenheit. So I'm just going to make note of that. And let's define a function, capital T of t. It's going to be a little bit confusing having capital T and little t. So capital T will be temperature, little t will be time. So this will be the temperature of the coffee. And it will be measured in degrees Fahrenheit, just because this thermometer measures in degrees Fahrenheit. So degrees Fahrenheit, and it'll be at time t, where time is measured in, let's say, minutes. Okay, so we also observed that t of 0 is 144. And so our goal is going to be to predict the temperature of the coffee. Let's say at the end of this lecture. So the end of the lecture. Okay, so there's a physical law that's relevant here. So let's just say the relevant physical law is going to be Newton's law of cooling. Okay, so what does Newton's law of cooling say? So it says the rate of change of the temperature of an object is proportional to So this is already starting to sound like a differential equation, right? We're talking about a rate of change being proportional to something. So what is it proportional to? It's proportional to the difference between the temperature of the object and the ambient temperature. Okay. Ambient temperature just means the temperature of the surroundings. So this is Newton's law of cooling. That's clearly relevant to our situation here, right? So we want to measure a temperature of this coffee. So that's going to be our object. Okay, so let's try to write a differential equation. In fact, we already have. This is a differential equation in words, just as most physical laws are. So let's just try to translate this into mathematical symbols. So it says the rate of change of the temperature, in other words, d capital T dt, right? That's the rate of change of the temperature, is proportional to equals k times. And what is it proportional to is the difference, so that's a subtraction, right? So we're going to subtract the temperature of the object and the ambient temperature. So there's a little bit of ambiguity here. So it looks like I could do that either way, right? So let me just write one of them down. So let's say temperature of the object, which is this function t, right? At any time, this is the temperature of the object. minus the ambient temperature. So I'll just call that T sub A for the ambient temperature. Okay, and I mean, technically this could also be a function of time. But in our case, I measured it earlier, and this is actually just going to be 75 degrees for us. So it'll be 75 degrees Fahrenheit. Okay, so that'll just be a constant. And there's one thing I may or may not need to change. So again, yeah, should I have it in this order or the opposite order? So let's actually think about this. And here's how you'd think about it. Okay, so let's say that our initial temperature of the coffee is hotter than room temperature, which it is in our case. So let's say this capital T at time 0 is going to be greater than 75, which means this is going to be a positive number, right? And I mean, we want K to be positive constant always, that's our convention. So this whole side will be a positive number, and that'll be telling us that the rate of change in the temperature will be positive, which is actually exactly the opposite of what we want, right? Because if our coffee were indeed hotter than room temperature, then it should be cooling down. Its temperature should be decreasing. So this should actually be a negative number, not a positive number. And so if we want to make this correct, we should actually have to add a minus sign here. And likewise, if our temperature of the coffee were cooler than room temperature, say it was iced coffee, right? This would be smaller than the TA, and so this difference would actually be a negative number. But then we are multiplying that by this negative, right? Negative K, so that'll actually be a positive number, telling us that the coffee will be, the temperature of the coffee will be increasing, right? The rate of change will be positive, which is exactly what would be happening, right? If it started out cooler in room temperature. So this is the correct differential equation. I should have this minus sign here. And maybe a better way to write this is, I'll get rid of that minus sign. I'll just put it inside the parentheses. So we have K times, and then I just switch the order of these two. TA minus T. Great, so that is the Newton's law of cooling differential equation. And in order to solve our problem, we're actually going to need to solve this differential equation. So let's go ahead and do that. So okay. So we're going to use separation of variables. Okay, and how is that going to work? So, well, first of all, can we use separation of variables? That's the first question we should ask. And the answer is, of course, yes, because our function only involves capital T on this side. So we could just divide this whole side by this function. And we'll get all the capital T's on this side, all the little t's on this side. All right, so let's divide by capital TA minus T. I guess I can leave the K on that side. And then I'll multiply by d little t. So I get this. So I separated the variables. That's the first step. Then what do I do next? I integrate both sides. This side with respect to capital T, this side with respect to little t. And it's actually going to give me what? So on this side, I'm going to get the natural log of absolute value TA minus T. But I need a minus sign, right? From this minus sign here, let's just check. If we take the derivative of this, then we get 1 over TA minus T. But because of the chain rule, we need to multiply by a -1. So that's why we have this minus sign there. Okay, and then what do we get on the other side? We get KT plus C, right? We need an arbitrary constant in there somewhere. And let's go ahead and solve this for capital T. So it's the natural log of absolute value. And then the minus sign comes on this side. I can just write plus c again. I don't need to write minus c because minus c and plus c are both just as arbitrary, right? So technically I'm replacing c with minus c here. Then we take we exponentiate both sides. So we get this absolute value equals e to the power of negative kt plus c, all in the exponent. But we can rewrite this side, right, as e to the negative kt times e to the c. And actually, I'm just noticing it's about time. I'm actually going to make one more observation here. Sorry about that. I was shaking the camera a little bit. Let's see. So I don't know if we can see this clearly. The temperature is now 136 degrees. And that's about 10 minutes after I made the first observation. Okay. I'm just going to make note of that up here. So T of 10 is 136. Okay. I'll say in a second why we need both those measurements. Okay, where were we? So, right, we can rewrite this side. Let's also get rid of these absolute value bars. And in order to do that, recall from last lecture, we need to add a plus or minus to this side. But we can just call plus or minus e to the c. I'll rename that capital A, just as we did last time. So I'm replacing, I'm letting A stand for plus or minus e to the c there. And finally, let's solve for capital T. So we get capital T equals, I guess it would be T sub A minus A times e to the negative kt. And, in our example, this is a number 75. So 75 minus A times e to the negative kt. Okay. What's next? So we actually have A and K here. We don't know what those are. Those are supposed to be just fixed constants for us, right? This is our function, by the way. This is our solution. So these are supposed to be fixed constants. We don't know what either of them are. That's why we actually made two observations here. So we observed the temperature at time 0, we observed it at time 10, and that's actually going to be enough information to figure out what both A and K are. So let's see how that works. So first I'm going to use, so let's use the initial conditions. Right? So I'm going to use T of 0 and T of 10, these known values, to find A and K. So first of all, it's always easier to start with T of 0. So T of 0 equals 144. Well, what is that telling us? That's telling us that 144 is going to equal 75 minus, and what do we have over here? So this little t is 0, e to the 0 is 1, so we just get 75 minus A, right? Which tells us that A is, let's see, what is it going to be? It's going to be a negative number, right? So A is going to be negative 69. Okay, so let's go to a new page. And let's update our solution here. So we now have capital T of t is 75 minus 69. So it's 75 plus 69 times e to the negative kt. Okay, that's great. We still have to figure out what k is though, but we also have this piece of information. Temperature at time 10 minutes is, what was it again? 136. Okay, 136. And what does that tell us? Well, we'll just plug in 136 there for, right here. So we get 136 equals 75 plus 69 times e to the negative k times 10, right? And k is the only variable left in this equation, so we can definitely solve for k here. Great. Okay, so first thing we'll do is subtract that 75. So we get 61 equals 69 times e to the negative 10k. So we get 61 over 69 is e to the negative 10k. Okay, then we'll take the logarithm of both sides. Natural log of 61 over 69 is negative 10k, which tells us that k is going to equal, I just divide by negative 10, so we get negative 1/10 times natural log of 61 over 69. You might be really alarmed here, right, because of the negative sign. We said that we set this up originally so that k should be positive. So did we set this up wrong? No, I think we did it right. So I see what's going on here. So this number here is less than 1, right? And so when this is less than 1, the natural logarithm will be a negative number. So this is actually this is a positive number, even though it doesn't look like it. Let's actually get an approximate value for that number. So I'm just going to plug that into my calculator really quick. Times the natural log of 61 over 69. And this number is approximately 0.012. Okay, so that's our value for k. So let's actually write out our solution. So the temperature can be modeled by this equation: 75 plus 69 e to the, let's put in this approximation, negative 0.012 T. Great, so this is actually, so this is our solution. And this right here can actually be used to predict the temperature at any time we want. We can just plug in any value for little t here, and we'll get the temperature. So for example, at time t equals 30, so we want the temperature 30 minutes after we started. What is the temperature t of 30? Let's plug that into the calculator really quick. So we have 75 plus 69 times e to the power of negative 0.012 times 30. And so that's approximately 123.14. Maybe too many significant figures. Just say it's about 123 degrees Fahrenheit. So this is our prediction. Okay. At time equals 30, at t equals 30. Okay, we're not that far into the lecture yet, so I still want to do one more example. So let's do the example, and then we'll come back and see how good our prediction was here. So this was Newton's law of cooling. So this is a typical example of a separable differential equation. Okay, so example 2 is going to be, this is a really cool concept. This is the concept of terminal velocity. We can understand this with separable differential equations. So you might have heard of terminal velocity before. For example, when a skydiver jumps out of an airplane, they start going faster and faster. But then there's a certain point at which they're going the same speed. They hit a maximum theoretical velocity, and they can't go any faster than that. And so that's the concept of terminal velocity. And let's see if we can understand this better through differential equations. Okay. So let's set up the problem. So let's say an object of mass m is falling toward the earth, or toward the ground. Okay, and then we're going to assume that the force due to air resistance, this is actually what's responsible for terminal velocity, so the force due to air resistance is proportional to the velocity of the falling object. Okay. And because it's air resistance, we also know that this force is going to act against the motion of the object. It's going to be acting in the opposite direction. So proportional velocity of the falling object and in the opposite direction. Okay. I guess we can draw a little picture here. So we have our object here, mass m, and it's always good the first thing you should do in these physical problems is pick a coordinate system. So here we're just going up and down. So we have to decide which direction we want to be positive. So I'm gonna actually choose down to be positive, just because that's the way it's naturally moving. But you can just as easily choose up to be positive, as long as you're consistent about the following choices. Right? So, okay, we're going to choose down to be the positive direction, and we have two forces acting on this object actually. Right? I mean, without air resistance, there's still some force that's causing it to fall to the ground, and that's the force due to gravity. So force due to gravity. And the magnitude of that force is mg, where g is the gravitational constant, right? Associated with the Earth. Okay. So g is approximately it's about 9.8 meters per second squared. Okay, and then we have the air resistance, and because the object is falling, that's going to be acting this way. So this is a force due to the air resistance. And that is going to be proportional to the velocity. So I have some constant of proportionality. I actually call that gamma usually. So this is, okay, so yeah, gamma times the velocity, v. So this is sometimes called the drag coefficient. Okay, and we're missing something, right? We need a minus sign here, because this force is acting in the opposite direction as the motion, right? So if v is going this way, the force will be going in the opposite direction. Same if v was going this way, right? If it were going if the object were moving in the negative direction, if v was negative, then this force will now be acting down in the positive direction. So we always need to flip the sign of v, right? So this is the force due to air resistance. I just want to point out that technically there's a more accurate model here, which is that this force is actually proportional to the square of the velocity. And it turns out that this is used in some situations. This is better used in some other situations. This is probably more accurate for our situation. The reason I'm picking this one is just because the math will work out simpler at this point. So let's now write a differential equation. So where's the differential equation going to come from? It's going to come from Newton's second law. But before I apply Newton's second law, I'm just going to write what the net force is on this object. So we're going to add both of these forces together. So the net force will be the force due to gravity, mg, plus the force due to air resistance, which is minus gamma v. Right? Okay. And Newton's second law what does that tell us? It tells us that this force is going to induce an acceleration, ma. But a is the derivative of v, right? So we can actually write this totally in terms of v. So it's m times dv dt. And so that's my net force is going to induce this acceleration. So I can plug this in for net force, and I get a differential equation. So we get m times dv dt equals mg minus gamma times v. Okay, so that's my differential equation. And my function I'm trying to solve for is v, the velocity of the object at any time. So let's go ahead and solve this. So is this a separable differential equation? Well, again, right, just like the last example, this side only involves the dependent variable v. So this is definitely separable, and here's how we do it. We just divide by this entire thing. Hopefully you're used to this idea now. This looks a bit weird at first, but something that you get used to soon enough. Okay, and so we separated the variables. Notice we just had one left over on this side. So I multiplied by dt, and I'm now going to integrate both sides, just like the last example. Let's actually go on to another piece of paper. So before I do that, let's actually write this a little bit nicer. So I'm going to factor out this m. So we get 1 over g minus gamma over m now times v dv equals this integral here, just of dt. And so what is this integral? Well, again, that's just a natural log. So we get a natural log of g minus gamma over m times v. But what do we need to multiply by out here? This time it's going to be negative m over gamma in order to cancel this out from the chain rule. Right? When we take the derivative of this, this is going to come out front, negative gamma over m. So we need a negative m over gamma to cancel it out. And on this side, we're just going to get t plus c, arbitrary constant. Let's go ahead and solve for v now. Okay, so let's try to do this quickly. So we have negative gamma over m times t. I can just write plus c again, right? Because technically I'm multiplying c by negative gamma over m, but that's just as arbitrary of a constant. And now we'll exponentiate both sides. So we get this times e to the c. We can get rid of these absolute value signs. It's very similar to the previous example at this point. Right? So I'll just replace plus or minus e to the c by a again. Okay. And what do I have to do next? So let's let's subtract the g. minus g. And then we'll multiply by negative gamma over m. And then we should be done. So our function of v of t is, okay, well again I can replace this a with a times negative m over gamma. This one I cannot replace, right? Because these are all fixed constants, right? Gamma, m, and g. So what do we get here? We get mg over, so we get plus mg over gamma. Okay, and I'm just realizing it's time to actually check the temperature. So 30 minutes have passed. So let's see what the temperature is here. Okay, so it looks to be about 121 degrees. So what was our prediction? So our prediction was 123 degrees. So we're a little bit off, but it's pretty close. So the actual temperature was 121 degrees Fahrenheit. There are many reasons. Of course, it's not a perfect model, and yes, it's very rare that you get exactly 123. But this was fairly close, and Newton's law of cooling is definitely a good model for this kind of situation. Okay, so we have a little time left, so let's figure out, yeah, what's terminal velocity is all about. Right? So here's our solution. So this is our solution to the falling object problem. Okay, now what do we need to do? So we have this constant here, a. We don't really know what its meaning is. So let's try to pin down a value a. So let's actually suppose that we're starting at rest. Right? So suppose v of 0 equals 0. Okay. So we're just dropping the object from rest at time t. Then, what does that tell us? That tells us that 0 is going to equal, and again, e to the 0 is going to be 1, so we just get a plus mg over gamma, right? So that tells us that a is going to be negative mg over gamma. Right? So let's replace a with negative mg over gamma. So we have negative mg over gamma e to the negative gamma over mt plus mg over gamma. And this is supposed to represent the velocity of my object at any time t. Okay. So how can we see the concept of terminal velocity? Okay. Well, let's just recall what terminal velocity is. Right, it's the maximum theoretical velocity of this object. So the claim is that by looking at this equation, we should be able to tell that this velocity is actually going to approach a theoretical maximum value, right? So in other words, the limit of the velocity, this is what terminal velocity is. It's just the limit of the velocity as t gets large, so as t goes to infinity, right? Is going to approach a finite value, right? So what is that value? Okay, well, we can just look at our equation, right? So as t gets large, what's happening to e to the negative, this is a positive number here in front, right? Negative gamma over m is positive. So we get e to a very negative number, which goes to 0, right? So this is actually going to 0. So this goes to 0 as t goes to infinity, right? So what does that mean? Does that mean the velocity is 0? Well, no, because we have this plus mg over lambda, right? So this is actually, we have something going to 0 plus this fixed number here. So that's going to be our limiting value of the velocity. So what's going on here? So let's just sketch a graph. Okay. So this is time and this is velocity. Okay. So what does this graph look like, or what does this function look like if we graph it, right? So we're actually we have an exponential decay, but then we're making it negative. So that's actually going to flip it like this. So it's going to be starting negative and increasing, but then we're adding this mg over lambda to it. So it's actually going to be going like this. Something like this, okay? So that's what this function looks like. And there's going to be this imaginary line that's approaching. And again, that was what we found to be mg over lambda. Or over gamma, sorry. I just want to contrast this really quick. The picture without air resistance. Okay. So here's without air resistance. Okay. What is the velocity going to look like there? Sorry, I got a bit of a smudge there. Okay, well, in that case, the only force we're considering is the force due to gravity, mg, right? And so we have Newton's second law, which is just going to tell us ma equals mg, right? Or a equals g. So the acceleration is just g, which means the velocity, so a of t, is a constant, g. And then that means that v of t is going to be what? Well, it's going to be gt plus some constant, right? If we're starting at rest, that constant is 0. And so the velocity is just going to be a linear function, just a linear function. Okay. But with air resistance, we see that it actually starts out maybe looking roughly linear, but then it starts to bend and then approach this terminal velocity here. Right? So this is the, this line represents the terminal velocity. Okay, so next lecture we're going to continue with examples of separable differential equations.